3, 2, 1, now.
Deep learning algorithms are often based on convolutional neural networks. In computer vision, they have become the de facto state-of-the-art for solving complex tasks such as image recognition, classification, and segmentation. In the following video, we present a demonstrator for hand sign recognition implementing such computationally expensive convolutional neural networks on a novel class of massively parallel processor architectures called tightly coupled processor arrays. The shown demonstrator takes images from a standard USB camera. Based on a pre-trained convolutional neural network, CNN, for hand sign recognition mapped to a tightly coupled processor array that is prototyped on the shown FPGA board. A connected robotic hand shall imitate each detected hand pose of a person in the image in real time. In the following, we give an overview of the system implementation. First, the USB camera images are downsampled from a resolution of 480 by 640 to a resolution of 38 by 38 pixels inside an ARM-based processor system inside the FPGA. An 8-layer convolutional neural network implementing the task of the hand pose recognition has been mapped to the tightly coupled processor array, shown right for acceleration. For each frame processed, a detected hand pose is converted to a set of PWM signals that control 5 servo motors of the connected robot hand to initiate its imitation. Let's have a closer look at the core of the accelerator architecture, the TCPA. In contrast to standard CPUs, massively parallel accelerators like TCPAs consist of hundreds of small but tightly interconnected processing elements, in short, PEs. Due to this very high degree of available hardware parallelism, not only CNNs, but a wide range of nested loop programs can be efficiently accelerated on such processor arrays. Thereby, the input and output data of such loop programs must be provided from or to small peripheral I/O buffers surrounding the array. But a key challenge now is the efficient and automatic mapping or compilation of such algorithms onto a processor array. For explaining the required steps, we first take a short look at the structure of CNNs and subsequently at their mapping. A CNN consists of multiple layers of neurons, in particular so-called convolutional layers, pooling layers, and activation layers. Shown here is a convolutional layer representative also for other types of layers. An input image, shown in the middle, is convolved with a local operator, the filter, shown on the left. By moving the filter over the input image, an output image is created pixel by pixel. Herein, each output pixel is computed as the sum of products of filter coefficients and input pixel values. Finally, not only one, but multiple filters are applied to obtain a set of output images, also called feature maps. Now, let's see how these layers of operations can be efficiently mapped onto a processor array. In order to assign regions of convolutions to individual PEs, the input image is tiled into segments of equal size. These are streamed through the rows of the PEs, whereas the filter coefficients are streamed through the columns of the array. Thus, each PE is assigned those convolutions belonging to a certain filter, feature map, and a subregion of the image. In fact, the acceleration speedup scales nicely with the number of available PEs, as we will see next in the hand sign recognition demo in action. In the following, our goal is to evaluate the recognition quality as well as the performance of the neural network for hand pose recognition that has been trained using 10,000 pre-recorded test images. As for the performance, we compare a 4x4 PE TCPA implementation with one on the ARM CPU system. As can be seen, the ARM implementation requires approximately 45 milliseconds to process one image corresponding to a frame rate of 22 frames per second. Notably, this would be too slow to process the camera input in real time, as it is providing 30 frames per second. In contrast, the TCPA requires less than 1 millisecond, allowing the real-time processing of more than 1000 frames per second. Tightly coupled processor arrays, as introduced in this video, provide a great architecture for accelerating applications that can be specified by nested loop programs in general and deep learning applications in particular. Apart from offering impressive speedups, as has been shown, they also provide at least an order of magnitude higher energy efficiency over existing accelerator architectures, such as GPUs or multi-core CPUs, and are therefore an ideal choice particularly for embedded and low-power products.